Okay, so good morning everyone, and I guess this is the last topic of the course, and I'm not sure if this is the last class. Well, officially yes, but it's possible that I may not be able to cover some of it. So, I might take one extra class. If you want to come, you are welcome, but whatever I take in the extra class, that will not be covered in the exam for sure. Okay. All right. So, as I said to you in the last class, we want to discuss finite element discretization of equations of special Gauss-Rod rods. So, finite element discretization of equations of special Gauss-Rod rods. Okay. So, remember we already learnt in the class how to solve the equations of special Gauss-Rod rods, where we wrote the equations as a system of 13 first order ODEs, right, and we posed it as a boundary value problem, which could be solved using commercial package, for example MATLAB, right. Now, the today's technique is a different technique. We would solve it using finite element methods. Okay. So, as you all know, what is the first step when we want to solve anything using FEM, finite element methods? So, we write down the strong form of the equations and then we derive the weak form of it. So, that is the first step. Okay. So, the strong form of the equations are n prime plus n hat equal to rho naught a little r double dot. Okay, that is the linear momentum balance, and the angular momentum balance is m prime plus little r prime cross n plus m hat, that is equal to rho naught times the moment of area tensor I into angular velocity omega, and the whole thing and then dotted time derivative of that. Okay, so, that is the angular momentum of the cross section, and then we take its time derivative, that gives you the rate of change of angular momentum of the cross section. Okay. So, this is the strong form of the equation. And when we want to get the weak form, we multiply the strong form with test functions, right, or the variations. So, to the linear momentum balance, we are going to dot this equation with del r, where del r is nothing but the variation in r, u little r. And similarly, to the angular momentum balance, we are going to dot it with del theta. And again, this is the test function or variation corresponding to change in the variable theta. Okay. So, that is the test function slash variation corresponding to little r. And this is the same thing, but corresponding to theta. Okay. And the variable theta gives you the rotation matrix. How would that give you? you simply say the rotation matrix big R is equal to exponential of the skew symmetric tensor theta. Okay, so essentially this rotation, although it's a 3 by 3 matrix, it has only 3 unknowns in this theta vector. Okay, so that's the axis angle representation. Find the skew symmetric matrix of theta, exponentiate it, then you get your rotation tensor. All right. So little r and theta are our kinematic unknown variables for special Gauss-Rod rods, and del r and del theta are the corresponding variations in those variables. All right. So once we dot it with the test function, and then we also do the integration over the length of the rod. So it goes from 0 to L, and this also goes from 0 to L. Okay, and then we write them together. So this becomes rho naught A little r double dot del r plus rho naught I omega dot del theta. Okay, so I write this separately. This is a dynamic term. So I write the dynamic term separately, that goes from 0 to L ds plus the remaining term. Bring them on the other side, these things. So it comes with a minus sign then, minus 0 to L n prime plus n hat dot with del r and one more minus 0 to L m prime plus little r prime cross n plus m hat dot with del theta. Okay. So we wrote down the same thing over here, and we have added the two equations. And the next thing to do is to work out integration by parts, because as you see here, this n prime, for example, n is the contact force which depends on strain, and the strains are first derivatives in our kinematic variables r and theta. So when we take the one more derivative, this is essentially second order in little r and theta, right. So we want to pass one of the derivatives from here on to the test functions. That's how we get the weak form. So in the strong form, they are right now, in the strong form, they are second order derivatives in little r and little theta. And the whole idea of weak form is that we reduce the order of derivative. So therefore we pass these derivatives on to test functions, okay, so that the order of derivative reduces, and that is why we call it the weak form. All right. So this is, so we will call it as G for the weak form, okay. And this term that you see over here, that is the dynamic term, right. So we will call it G dynamic, G dyn, and this term that we see over here, that is G static, okay. But G static is not done yet, because we have to work out the integration by parts. So G static is then negative 0 to L. So, n prime dot del r. So, can we write that as n dot del r whole prime and then one minus sign n dot del r prime. What we had over there was n prime dot del r. So, when you expand this, you got two terms here, n prime dot del r plus n dot del r prime, which cancels with this term here. Okay? And similarly, you could also think of passing the derivative from little m prime on to del theta. And what we would have is plus m dot del theta whole prime minus m dot del theta prime. Okay? And then we look at the remaining terms, which are plus n hat dot del r plus m hat dot del theta, and one more term is remaining, which is this term. So, we simply write that over here, plus little r prime cross n dot del theta. Okay? And then look at this term, for example, n dot del r whole prime, which is being integrated. What is this going to give you? This will simply give you the thing inside the bracket at the boundary, right? So, you could further write it as 0 to L n dot del r prime. I am writing this term here, minus minus becomes plus, plus m dot del theta prime, that is the term over here, and then I will write this term, okay, which I will write as plus n cross, see this is little r prime cross n dot del theta with a minus sign. So, I could write it as n cross little r prime dot del theta, and then minus goes away. Okay. So, this n cross little r prime dot del theta. So, I took care of this term, then the term over here, the term over here, and then I write these terms separately, minus 0 to L n hat dot del r plus m hat dot del theta, okay, and then the boundary term, the terms from here and from here, which is going to give you, with a minus sign of course, n dot del r plus m dot del theta evaluated at 0 and L, isn't it? And you see the n and m's which are present here, they are at the boundary and they are the ones which are prescribed by the external agent. So, they do not come from constitutive law. We can't say that this n is equal to r times del psi over del v. It does not come from Rod's constitutive law, it comes from what we are prescribing. Okay? So, these are n p, I will just write it to differentiate n p and m p, the prescribed quantities. So, these are prescribed externally. Can't use constitutive law or relations, can't use constitutive relations here. Okay. So, we are further going to rewrite it. So, that becomes G static is then simply 0 to L n dot del r prime plus m dot del theta prime plus, and you see that is the scalar triple product, n cross little r prime dot del theta. So, I could also write that as n dot, or maybe that is already fine, n cross little r prime dot del theta. Okay. All right, yeah. So, I could also write that as n dot little r prime cross del theta. Can we do that? We just switch the dot and cross because it is a scalar triple product. So, we take care of the first three terms, and then we have remaining terms. Okay, and what we have to note here is that this term over here is also prescribed by the external agent, and this term over here is also prescribed by the external agent. So, these are the terms coming due to external loads. If it is not present, then this simply goes away. If there is no distributed load, n hat will go away, and if there is no distributed moment or couple, this also goes away. Similarly, if there are no prescribed and forces and moments, then these terms would also go away. All right, and this is due to internal response of the rod. So, we could categorize this. So, this is due to internal response and this is due to external load. All right. Yes.
Shouldn't we put an increment ds for each of the integrals?
Yes, of course. So, that is something I am not carrying along, but
Okay.
it is being integrated. So, there is ds everywhere because it is integrated with respect to s, the arc length. So, everywhere it has to be there right from the beginning. So, we had this ds here, which we missed out over here and over here also. So, that ds is everywhere, that is a variable of integration. Okay. Now I am going to write this in a more compact form, and I'm just going to introduce an operator which is called E transpose. Okay? This is an operator which is your identity, so which I'll write as just 1, not to confuse it with the inertia tensor. 1, the identity 3 cross 3 matrix, d over ds derivative, and little r prime is skew-symmetric, a skew-symmetric tensor formed by little r prime. All right. So, it is just an operator. Then what we have over here is a 0 tensor, and this is again the same 1 d over ds. Okay, so this is a 6 by 6 matrix, 6 by 6, and each of them are individually 3 by 3. All right, and this thing I will tell again is a skew symmetric tensor whose axial vector is little r prime. So, basically when this acts on any vector, it will simply become r prime cross that vector. That is why I have this cross also written here. All right. And what you would see is that when I use this operator here, then this term could be written as integral from 0 to L of n m dot E transpose del r del theta. Those 3 terms I could write it in a condensed notation like this. Why is that so? Maybe you can try to work out E transpose dot this. So, you take this matrix and multiply with this thing. So, I will work it out as a side calculation. So, when I work out this thing over here, that is simply 1 dds little r prime cross 0 1 dds multiplied with del r del theta, and just work out the multiplication and see what we get. So, when we multiply this times this, that gives us dds of del r, that is del r prime, and identity times del r prime, that is equal to del r prime. So, this gives us del r prime, this times this, then this times this. That is how we multiply, right? Matrix times vector, this into this. And now, this times this, because it is a skew symmetric tensor, it simply becomes little r prime cross del theta. So, over here it becomes little r prime cross del theta, right. And then the second term here, this times this, 0 into del r is 0, plus this times this is del theta prime. Okay. And you see, once we have worked out E transpose into this, then you have to further multiply with this vector n m. So, when you dot this with n and m, what do you get? N dot the first term plus m dot this term here. Can you see that we have the same thing over there? So, n dot del r prime, that is the first term over there, n dot little r prime cross del theta, that is the third term over there, and m dot del theta prime is the second term over there, right. So, when we use this operator, you could write this thing in a very compact form, and you will see that that operator will keep coming. Later on you will see it one more time. All right. So, we could write this term in a compact notation over here, and as Sebastian said, there is a ds, the integration variable. Okay. All right. So, that is the weak form, and maybe we can hold it a little bit and write that this weak form that you see over here, G is static. What does it depend on? The weak form depends on the unknown little r, theta, and also on the variations del r and del theta. That is it. If you know little r, little theta, then you compute the strains, then you use constitutive law, and you get your forces and moments. So, you see n and m are present here, and del r and del theta are also present here, as you can see here. And the nice thing to know or note is that this weak form is linear in variations. It is always the case. The weak form is always linear in variations, but non-linear in your unknowns. Non-linear in unknowns. Okay. So you have to understand that the weak form is this whole thing, this, and also your G dynamic. So that is a weak form, the full G. And if you are only working within a statics problem, then G dynamic is not present, and you only have G statics. Okay. So today we will assume that we do not have the dynamic term, so that we are only working out a static problem, how to solve a static problem. So we just have to bother about G static, this term that you see over here. And what we see is that G static is non-linear in our unknowns little r and little theta. So therefore, we have to linearize the weak form, right, because we can't solve non-linear equations. So you have to linearize it and solve it iteratively. So the next goal, of course, then would be to linearize the weak form, right. So the weak form holds for all del r and del theta, all right. So your G, when you had the strong form, you multiply with test function and then integrate, and then you set it equal to 0. So your G is equal to G static plus G dynamic, and that is equal to 0 for all del r and del theta admissible, for all admissible del r del theta. And you must have learnt in your FEM course what is the meaning of admissible del r, admissible. So, they have to satisfy some boundary condition, kinematic boundary condition. All right. So, admissible means it should satisfy the kinematic boundary condition. And as we said, we are only going to focus for today on the statics problem. So, we get rid of this, and our G static now, as we just wrote down over there. So, G static is non-linear. So, it has little r, little theta, and del r, del theta. So, we want to find out little r and little theta, so that G static is equal to 0 for all del r and del theta. So, that is the question we have to solve for, but sadly this weak form is non-linear in little r and little theta. So, it becomes difficult, and therefore, we have to linearize the weak form. Okay. So, to linearize the weak form, we have to get its kind of first derivative. So, we are going to state that you have r epsilon, which is equal to little r plus epsilon times delta r. Okay, so that is how we change, that is how we increment your little r. And similarly for your theta, so your rotation tensor big R epsilon is equal to exponential of epsilon delta theta times big R, which is simply exponential of theta. So, that means your delta r, that is the increment in little r, and delta theta, that is the increment in theta. Okay, but it is not like nu theta is equal to theta plus epsilon delta theta, because thetas do not simply add. You have to work out the exponential and that get your big R epsilon. Okay. All right. So, that means we want to write down our G static at little r epsilon comma little theta epsilon and del r del theta. So, that would be equal to G static at epsilon equal to 0, which is little r comma little theta. Okay. I can maybe further write it down that this big R epsilon is exponential of theta epsilon. So, you see, therefore, we can't say that theta epsilon is equal to theta plus epsilon delta theta. So, that is wrong, because it is the exponentials which are related this way. And this is without the exponential. So, you can't write this. Okay, so, your G static for any epsilon is this, which is equal to G static at epsilon equal to 0 plus the first derivative with respect to epsilon dg over d epsilon. at epsilon equal to 0 times epsilon plus the higher order term. And if you want to just linearize your weak form, then we just stop here, and this is a higher order term which we forget about. We just forget. And that's a linearized form. Okay? And see, our goal is to solve the nonlinear weak form. So, we want to set this, we want to find out little r epsilon and little theta epsilon for which this is equal to 0. But that's a difficult question, that's a difficult problem. So, what we would do, we would solve the linearized form. So, we would set this equal to 0. And solving this, so this then becomes, this is not equal, this is almost equal, because we only think of the linearized term. But the nonlinear weak form is difficult to solve. So, we first linearize and solve the linearized problem. We set this equal to 0 and get our delta r and delta theta, the increments. But we have only solved the linearized weak form, we have not solved the nonlinear weak form. So, what do we do? Once we get our delta r and delta theta from the linearized weak form, we find out the new little r and little theta, we find out our little r epsilon, little theta epsilon, plug it in the weak form and see whether it is equal to 0. If it is not equal to 0, then we further linearize about the new state. See, that is how we solve nonlinear equations, isn't it? So, I hope you guys know how to solve nonlinear equations. No? How many of you do not know? Anybody knows? Kind of, okay. See, why we are doing it? Solving linear equations, that we know how to do it. Why? Because it's simply a matrix equation, you can invert your matrix. Do you know how to solve this problem? A x equal to b. A is a matrix, x is the unknown, b is another vector. Then what is x equal to? That is simply A inverse b, right. So, we all know how to solve. So, this is a linear equation, because it is linear in the unknown x. So, there is a definite way to solve linear equations, x equal to A inverse b. But when we have nonlinear equation, then we do not know how to solve it. Just think of log x equal to, let us say, or log x plus x equal to 3, and I want to find out x so that this is satisfied. Can you solve it? We have to first see that this is nonlinear in x. If you double your x, does this thing become double? It does not. Log of 2x is equal to log of 2 plus log of x. So, it does not become 2 times log of x. Log of 2x is not equal to 2 times log of x. So, it is not linear in x, it is non-linear, and we do not know how to solve it in a simple fashion. So, there is something called Newton-Raphson scheme. Are you aware of that? Newton-Raphson method? Okay. So, we use Newton-Raphson method. to solve nonlinear equations. And what's the idea behind Newton-Raphson method? Let us say that's your f of x, which is equal to, in this case, log x plus x minus 3, and we want to get it equal to 0. So the idea behind Newton-Raphson method is we linearize the nonlinear equation first about some initial guess. So that's your f of x. So what we would do is we write f of x as some f of x naught plus f prime of x naught into x minus x naught, just simple Taylor's expansion, plus the higher order term, but we forget about the higher order term because we are just linearizing it. And this would be fine if your x and x naught are very close to each other, which means if x minus x naught is very small, then you look at the higher order term, it has x minus x naught square, x minus x naught cube. So higher order terms become still smaller and smaller. So if x naught is very close to your solution, then this is really nice. So the nonlinear expression can be very accurately approximated with a linear form if x is very close to x naught. And you see, although we don't know how to solve this equal to 0, but the linearized equation we know how to solve it, because you see this is simply x equal to x naught minus f at x naught divided by f prime of x naught. See, it's, if you want to solve this and get your x, that's what it is. But we have solved the linear equation, we had to solve the nonlinear equation. So what we will do is, once you get your x, then you check whether f of x for that x is equal to 0 or not. If it is not equal to 0, then what you say is your x naught, so your x naught, your new guess is now your x itself that you obtain now. So x naught then becomes x, and you further linearize it about new x naught. See, that's your old x naught, and this gives you new x naught. You further linearize this about the new x naught, and again solve for new x. So you keep on doing it until your f of x becomes equal to 0. So that's your Newton-Raphson scheme. Okay, you can of course go to Wikipedia also and learn about this. They are very, it's very condensed, maybe just half page you have to look at, and you can know how to solve, how Newton-Raphson scheme works. All right. Okay. So our equation is also nonlinear. You see, your weak form is nonlinear in the unknown little r and little theta. So we have to use kind of Newton-Raphson scheme. So whenever you have a nonlinear equation, you can always take it for granted you have to linearize this whenever you have nonlinear equation. So, here also we have nonlinear weak form, there we have to, therefore, we have to linearize this. Why linearize? Because linearized equations are straightforward to solve, but then it becomes iterative, as you saw here. Although you could solve for x, but then you have to again linearize and get again your x, keep on doing it until your f of x becomes 0. So, that is how you solve nonlinear equations. So, similarly over there also, that is how we would solve the nonlinear weak form. Okay. So, as we saw, the first step is to linearize the weak form, and that you see over there. The linearized form has got g and dg by d epsilon at epsilon equal to 0. So, we have to now evaluate that linearized the first derivative with respect to epsilon, because we already know how does your g look like, right. We had that expression for g. Now, we want to get the expression for dg by d epsilon at epsilon equal to 0. All right. So, I will just write down again, your g static was 0 to L n m dot E transpose del r del theta, right, and then you had the external terms also. Maybe I will write that down, minus 0 to L n hat m hat dot del r del theta minus n p m p dot del r del theta, but only at the boundary 0 1. All right. So, we have to now linearize this. Let us assume that your n hat and m hat are 0. For now, let us assume you do not have distributed loads and distributed moments. So, we can get rid of this. If it is not, then you have to also work it out, but let us suppose this is not there. So, we forget about this, and this is the most crucial part to linearize. These are not so difficult to linearize, but this is the most crucial part. So, how do we linearize this? So, we have to first work out that epsilon business. So, we get g static epsilon, which is equal to 0 to L n epsilon m epsilon. As you change your configuration, little r changes to little r plus epsilon delta r, and theta changes to theta epsilon, the forces and moments will also change to some epsilon, isn't it? As you change your configuration, the strains change, and therefore forces and moments also change. So, this epsilon is just denoting that change in forces and moments. Dot with E transpose, and that also will have epsilon, because you remember that your E transpose operator had little r prime cross. So, because of that, this also gets one epsilon multiplied by del r del theta, but this does not get any epsilon, because these are variations, they do not change with epsilon. And then we have to find out d by d epsilon of this. So, d by d epsilon G static epsilon at epsilon equal to 0. So, what is that going to be equal to? So, there are two things which depends on epsilon. So, we have of course have to use the product rule. So, we first work this out, d by d epsilon of n epsilon m epsilon at epsilon equal to 0 dot with E transpose del r del theta plus 0 to L n m dot d by d epsilon of E epsilon transpose times del r del theta. Okay. All right. So, now we have to understand how to get this term. So, we have to work out this term and of course, this term over here also. So, any idea how to work this out? So, maybe we can look at them, each of them individually for forces and also for moment. So, what is d by d epsilon of n epsilon? So, we have to expand your n epsilon. So, that is d by d epsilon of big R epsilon times del psi over del v at v epsilon comma k epsilon. That is what this is. N is equal to R times del psi del v, right. So, big R at epsilon into del psi by del v at epsilon strains. So, you see all of them are changing. So, here again you use product rule. So, d by d epsilon of big R epsilon, what is that going to give you? So, this is equal to d by d epsilon of big R epsilon times del psi over del v plus big R times d by d epsilon of del psi over del v. What is d by d epsilon of big R epsilon? Now, big R epsilon, you can see that is this, and when you work out d by d epsilon of that, we had worked that out while doing the minimum potential energy method. You had the energy of the rod, and when you took its first variation, you remember, then you found the Euler-Lagrange equations, and then you got that n is equal to R times del psi del v and m equal to R times del psi del k. So, that day when we were working out, we had found out that d by d epsilon of big R epsilon. I will just write that here. So, d by d epsilon of big R epsilon, that is simply d by d epsilon of exponential of epsilon delta theta times big R. So, essentially we have to work out d by d epsilon of exponential of epsilon delta theta into R. And when you expand this exponential in Taylor series identity plus epsilon delta theta plus epsilon square delta theta square by 2, keep on doing it, and then take d by d epsilon and at epsilon equal to 0, then only delta theta survives, and you get delta theta times r. Okay, so that's what you will get. And then you also have to work out, you see this term, d by d epsilon of del psi del v. Now, what is that going to be? D by d epsilon of del psi del v. So, that is nothing but you have to use chain rule, because psi depends on v and k. So, it becomes del 2 psi over del v into dv epsilon by d epsilon at epsilon equal to 0 plus del 2 psi over del v del k into dk epsilon over k d epsilon at epsilon equal to 0. Now, do you guys remember we had also worked out the linearization of the strains v and k that day. So, linearization of strains. So, d v epsilon by d epsilon, which is nothing but d by d epsilon of big R epsilon transpose into little r epsilon prime. And when you work this out, which we had done in the last class, in that class, this was equal to big R transpose times delta little r prime plus little r prime cross delta theta. Okay, you just have to go back and you can see these steps involved. And similarly, for your curvature k, dk epsilon over d epsilon at epsilon equal to 0, that is equal to big R transpose times delta theta. Okay, so this is what we have to plug in. So, we have to plug in this term, then this term and this term in the first expression over there, and let us see what do we get. Okay, so when we combine all of them together, then we are going to get delta theta times big R times del psi over del v. That comes from the first term over there, and the second term is then going to give you plus big R times del 2 psi over del v 2 and del 2 psi over del v del k multiplied with big R transpose of delta r prime plus little r prime cross del theta and big R transpose of delta theta. Okay, I have missed out this delta theta prime here. This should be a prime. So, that is a prime over here. Can you see that? This is what it is. So, you multiply this times this. So, del 2 psi over del v 2 into this thing, because you have del 2 psi over del v 2 into dv by d epsilon, which is this number. So this number I have put over here, and this number I just put it over here. Okay. All right, and then you further see that this is delta theta times big R del psi by del V. What is big R del psi by del V? That's nothing but your force N, right? So that's delta theta into N, but delta theta is a skew symmetric, so it becomes delta theta cross N, or minus N cross delta theta, right. So this term is same as minus N cross delta theta, whereas this term over here is as it is. Similarly, when you work out d by d epsilon of m epsilon at epsilon equal to 0, because you have both of them, n epsilon and also m epsilon, what's that going to give you? You know, it's going to be exactly the same way, because m epsilon, when you go over there, that will be big R epsilon times del psi by del k instead of del psi by del v. And then when you come over here, you have del 2 psi by del k del v into dk by d epsilon plus del 2 psi by del k into dk by d epsilon. And then you have to use the same derivations. And when you do that, your first term will be minus m cross delta theta, and then the second term is going to be your big R times del 2 psi over del k del v del 2 psi over del k times the same thing that you have over here, the same thing. Okay. You know, now having worked out them individually, I like to recombine them just as it is over there. Maybe before doing that, we can also work out what is this thing over here. So can you guess what is that going to be? D by d epsilon of E epsilon transpose. So you see inside this operator, what was the function of epsilon? Only the term over here. This was identity times d by ds, identity times d by ds, this was 0. So identity times d by ds, when you take its d by d epsilon, it goes away. So it's simply 0. That's also 0. That's also 0. But over here, you just get delta r prime cross. So instead of little r prime, it becomes delta r prime. Okay. Now let's combine them and see what we have. So we write it again, d by d epsilon of g is static at epsilon equal to 0. Can you see what this could be? You see the first term, this is there and this is there. So of course that could be your first thing to write over here. And you can maybe write like this, you see 0 minus n cross, then 0 minus m cross times delta r delta theta. Can you write that? See, when you work out this times this, it gives you minus n cross delta theta, isn't it? And that's what you have, minus n cross delta theta. And the second term is minus m cross delta theta. So that's the first term. Then the x remaining terms, let's see how that can be worked out. See, I'm going to write it as plus big R times 0 times 0 times big R into del 2 psi over del V2 del 2 psi over del V del K del 2 psi over del K del V del 2 psi over del K, okay, times the thing that you see over here. And you will be surprised that this is same as big R transpose 0 0 big R transpose into, so you see all the matrices are there, you get another matrix which is nothing but your E transpose multiplied with delta R delta theta. You see, when you work out E transpose into delta R delta theta, that's going to give you the thing inside the bracket over here and this delta theta prime. And it then gets pre-multiplied with this matrix so that you get big R transpose and big R transpose over here. See, maybe let me work this out. This thing over here, can we say this is same as big R transpose 0 0 big R transpose times delta R prime plus R prime cross delta theta plus into delta theta prime. Can you say that? When you multiply this with this, you get exactly what it is over here. And this thing that you see is same as E transpose into delta R. With that definition of E transpose, when you multiply with this number, this vector, you get this thing. So you see this E transpose came again. So you had this thing coming here, but then the whole thing, you see, this has to be dotted with this number. So this whole thing is then dotted with E transpose times del R del theta. Isn't it? Quite simple. And then we think of the last term over there. What is that going to give us? You see, in this green circle, you put this thing, and can you guess what you get? So that's your side calculation. Plus, for the last term over there, maybe I'll just write here, dot with that number which is 0, 0, 0, delta little r prime cross del r del theta. And when you work this out, what does this give you? This times this is simply delta little r prime cross del theta, and this times this is 0. Then you multiply with this, then m dot 0, that's not there, but n dot this thing. So what you get is simply n dot delta r prime cross del theta, n dot delta r prime cross del theta. So I write the same thing again. So this is d by d epsilon of g static at epsilon equal to 0. So that's over here, which is 0 to L of 0, 0 minus n cross minus m cross times delta r delta theta dot with E transpose del r del theta. So I am just going to separate it, dot E transpose into del r del theta plus 0 to L, the other term. And now I am just going to introduce some compact thing. So what you see over there, big R 0, 0, big R, I am going to write pi for it, pi. So it's a 6 cross 6 matrix, I just call it pi. Okay, so that becomes pi 6 cross 6 pi matrix of rotation times, you see that second derivative, that's actually the elasticity tensor for rods, which contains the information of stiffnesses. So I am going to write that as h, okay, pi times h. And what's that? Pi transpose, right? If this is your pi, then that's suddenly pi transpose. So you get pi transpose then E transpose into delta r delta theta dotted with again E transpose del r del theta, isn't it? Plus the last term, which you could also write as, see it's simply a scalar triple product, n cross delta r prime dot delta theta. So this becomes your n skew symmetric, n skew symmetric times delta little r prime dot delta theta. Okay. So that's the linearization of the internal response of the rod, and then you would also have linearization from distributed load plus linearization from boundary term. Okay, which we are not working out, but one can do that also from boundary terms. Okay, so that's a linearized form. So just to give you a recap, so we had your G at your little r epsilon, little theta epsilon, and del r del theta, which you could also think at as some G of delta r delta theta little r little theta del r del theta. I'll just tell you what I'm writing here, which is equal to, so that's approximately equal to G at little r little theta del r del theta plus your dg of delta r delta theta little r little theta del r del theta. So that was your non-linear weak form with your epsilon, and since little r epsilon is little r plus epsilon delta r, so I just wrote the same thing over here, but explicitly showing delta r and delta theta. Okay, and this you already have expression for this, isn't it? So this, if you remember, was 0 to L n m dot E transpose del r del theta. So that's your G. Okay, and it also had this extra plus terms due to, or maybe I could just write it here, minus 0 to L n hat m hat dot del r del theta minus np mp dot del r del theta, but only at the boundary. So that's your G. So if you want this, you have to get this n and m at epsilon, and the same thing is also, it's the same expression, but at epsilon equal to 0. So this is at epsilon equal to 0. So you will have n without epsilon, but the same expression. And this term over here is this thing on the top, dg. And you see the way I have written here, this dg, you would also be able to note it is, this is linear, it is linear in delta r delta theta, it is also linear in del r del theta, but it is non-linear in r theta. Yes?
So in the upper row,
Yes.
delta theta, this must be a lowercase delta, isn't it? Last
Oh
one.
yes, it is del, that is true. Thanks. This is del. The variation theta. You have a very sharp eye. Okay. So that's the linearized. See, this is a linearized term which is linear in the increments delta r delta theta, and also linear in the variations del r del theta. Okay, so right now this is in a functional form. We want to extract some matrix equation from it. You remember how to solve that Newton-Raphson equation? You had matrix times the increment equal to something. So our goal is to get the increments delta r delta theta so that this is equal to 0. So instead of solving this thing equal to 0, which is non-linear, we will like to solve the right hand side equal to 0 for delta r and delta theta, and it is linear in delta r delta theta, which are your unknowns. So you see, you have converted your problem as a linear problem in a different unknown, delta r delta theta. And linear problems are straightforward to solve. So the next thing is, once we have got the weak form, then we had the linearized weak form. So what's the next step in any FEM method? Yeah? Discretization of the weak form, because then only you can extract your matrix equation from there. So now we talk about discretization. So what we do is, we have our rod which spans from 0 to L. So we are going to discretize into nodes. So node number 0, 1, 2, 3, 4, up to last node, which is big N. So there are total n plus 1 nodes, and n elements, element 1, 2, 3, 4, 5, 6, 7, 8 up to n. Okay. And then, so this is the discretization of the domain. So this is discretization of the domain of the rod. Then we have to discretize our variations and the increments. So you will write your delta r, which is your increment. So you will, which is a function of s, isn't it? So we are going to write it as some delta r I n I of S. So, where n i's are your shape functions. Okay. So, this S dependence has all moved on to shape functions, and delta R i's are simply some constants. They are not functions of S. All the S dependence has moved to shape function. Okay. Similarly, for delta theta, we say that's also approximated by delta theta I n I of S. These were for increments. Then we talk of the residuals, sorry, of the perturbations or variations. So, that is del R of S, that also we approximate as some del R I times n I of S, and then del theta of S also as some del theta I times n I of S. Okay. So, n i's are your shape functions, and you might be knowing about the properties of shape functions. So, shape functions are associated with each node. Shape functions are associated. See, there is an I running over, n of subscript I. So, I goes to each of the nodes. Okay, so shape functions are then associated with every node, and it is such that n I of S, for example, would be equal to 1 at node I, but that is equal to 0 at all other nodes. So, that is the property of shape functions. So, for example, if I want to draw my shape function, so here is a 0, node 1, node 2, node I minus 1, node I plus 1, and going up to node n. Then the shape function n I will be 1 over here. So, I am drawing n I, it is 1 over here, but 0 at every other place. So, it is going to be something like this. And it could be varying linearly over here or in a nonlinear fashion, depends on the shape function. If you have a linear shape function, then it is going to vary linearly over here, but it will always follow this rule. So, that is your shape function n I. If you talk of shape function n I plus 1, then it is going to be something like this, I plus 2. So, that is your shape function n I plus 1. So, with that as your shape function, can you see what is the meaning of delta R I, delta theta I, del R I, del theta I? Just evaluate, for example, delta R at S I. Okay. What is the value of delta R for S of the node I? So, that is simply, maybe make it J, that is delta R I n I of S I, sorry, S j. But what is n I of S j? N I is equal to 1 only at S I, at node I, but it is 0 at all other nodes. So, what is n I of S j? It is 1 if I equal to j, otherwise 0. So, it is delta I j, right, Kronecker delta. So, that is equal to delta Ri times Kronecker delta Ij, which is same as delta Rj. So, what you see from here is that delta R at Sj is equal to delta Rj. So, what is the meaning of these coefficients then? The meaning of these coefficients are simply then the values of these variables at the corresponding nodes. So, delta Ri is then the value of delta R at node I. Similarly, delta theta I is the value of delta theta at node I, and likewise for del Ri and del theta I. Okay. So, that is the nice thing about choosing these kind of shape functions. If you have a shape function which follows this rule, then the coefficients have got physical meaning. Okay. So, if for example, you want to, let us say, draw delta R with that expansion, and that is your 0, 1, 2 up to n. So, you will have delta R1, delta R2, maybe delta R3, delta Rn. So, that expansion will be such that these numbers will give you value of delta R at the nodes, but in between the nodes it gets interpolated through the shape functions. Okay, so, in between the nodes it will, if this is delta R0, then it just gets interpolated. But at the nodes it gets a value from those coefficients, and between the nodes it just gets interpolated. If your shape function is linear, then you just have to add straight lines between the nodes. All right. Okay, so I see that I am already running out of time, and I certainly need one more class to finish this. When do you think we can meet for the next class? So, maybe let's stop here for the recording purpose.